Hello everyone, my name is Qing Yin, a postdoc in Columbia University. Today I will talk about a dual skeleton framework for the freezing and thawing of multi-phase porous media, collaborated with Hyun-Sung Su and advised by Professor Wai-Ching Sun in Columbia University. Before I start, I would like to talk about Professor Frank DiMaggio. So he's very famous for developing the CAP model for the inelastic constitutive behavior for soil. And unfortunately, I don't have a chance to meet him in person, but I do have some indirect connection with him. So this is a photo from 2013 Built lecture in Columbia University, where Professor Bohar here gave the lecture. So in 2014, I came to Stanford to study with Professor Bohar on constitutive formulation modeling for shale. And it is quite related to Professor Frank DiMaggio's work. And now I come to Columbia University, where Professor DiMaggio teach and do research. And now I work under the supervision of Professor Wai-Ching Sun, also in this photo here on the right. So it's quite a great honor for me to be here to celebrate his birthday as well. So let's start. So why freezing and thawing of soil is so important? Of course, it can cause a lot of damage to engineering practice. For example, the thawing settlement in the left can cause the settle of the ground. And also freezing soil underneath this pavement will cause so-called frost heave in the road, which means so the freezing soil expands underneath. This is quite common in a cold area like Alaska. Current models consider ice as a composition similar to a pore fluid. So it's a composition of pore. So the ice cannot sustain any shear stress. And also, even though ice is viscous, very commonly known to us, but the viscosity of ice is not generally considered in the freezing and thawing of soil. Also, anisotropy is not currently captured by models, but it has been observed in experiments. And in this photo, the ice lenses grow out of the ground in Sierra Mountain in California, clearly show that ice has a preferred direction of growing. Also, our approach is like this. So we have the multi-phase decomposition other than the traditional volume fraction Phi-S, the soil, Phi-C, the crystalline ice, and Phi-L, the volume fraction of the water, liquid water. So we also define the volume fraction of soil and the ice relative to the total volume of the solids. These two parameters will be used for dual skeleton constitutive modeling later. For convention, we have the degree of liquid and ice saturation. This is the liquid saturation, ice saturation. And by defining those parameters, we can also relate them together. And we have this partial and intrinsic density defined here. The partial density can be related to intrinsic density in this formulation. So the set of conservation laws we use is actually an approach that is a fully coupled thermal hydromechanical approach. First, the set of equations balance of mass for each phase. So for ice and liquid, we have this rate of phase transition. When ice forms, we assume the solid skeleton and ice share the same velocity. So the material time derivative only influence the liquid, and we combine them together to get this balance of mass equation. Also, we have this straightforward balance of linear momentum equation. So here the pore pressure is only the pressure of the liquid water. And we also have the balance of energy, which is quite a standard. We have this homogenized heat capacity CF, homogenized thermal conductivity. So having those conservation law, we look at this constitutive law for dual skeleton. From these photos from our collaborators, when ice form from the bottom to the top, actually the ice lenses those long fiber-like material penetrate in the voids of soil. And the soil and the ice crystal each form a separate skeleton. They seize each other very tightly. So we can assume that their strings are the same and equal to the homogenized string. So in this assumption, displacement field across the boundary of two skeletons are also continuous. And the force balance is also naturally satisfied. So we use this dual skeleton formulation developed by Bohar et al. In 2020. It has the string decomposition for the soil is just elastic and plastic, but for ice it's elastic and viscoplastic. We have this stress decomposition, intrinsic stress related to elastic strain, and we have this homogenized relations. For detail, you can refer to this paper. Ice, the most common form of ice crystal is actually called the IH. It's called 1H, hexagonal crystalline structure, which is transversely isotropic. It is defined by a bedding plane and also the bed normal direction, the vector n. So this structure can be represented by a microstructure tensor. You can find the details in Sam Nani's paper. And also this elastic tangent operator have 5 independent parameters for transverse isotropy instead of 2 for isotropic elasticity. And for the plastic and viscoplastic part, we have the modified chem-clay model. For the anisotropic crystalline ice, we have this projection tensor project the stress into a fictitious stress space. You can find details here. And for viscoplasticity, we use the Perzina's overstress model, which includes a parameter called viscosity of ice. This is related to time. And the hardening law is quite standard. So for the retention part, our former group member Na and Professor Sun, you proposed using the ice pressure related to water pressure using the Clausius-Clapeyron equation. But here in our current formulation, the ice pressure is directly calculated using our finite element simulation. And the cryosuction here, the capillary effect is independently caused by the gradient of water pressure instead of the previous approach that is manually defined. So let's look at 2 examples. First is 1D freezing. We have a cylindrical sample which is fixed at the bottom and the lateral displacement fixed. It is initially at 2 degrees, and I apply a temperature -8 degrees on the top. So the freezing will start from top to bottom. We allow water supply at the bottom. Here are the results. So as time goes by, from 1 hour to 10 hours to 20 hours, we can see that the freezing zone develop deeper down. And along those freezing front, this transition zone, we can always see a porosity has a heave here. This is a result of competing of freezing, which reduce the porosity, and the cryosuction induce a fluid flow into the region, which increase the porosity. So in the freezing zone, we have this viscoplastic spring capture here. And also from this plot, we can see the freezing always happens when temperature is below 0. So for the above 0 part, there's no ice freezing. Second example is the Sowing consolidation. We have a 2D sample supported on roller, and we have this lateral displacement constraint. The sample is actually initially frozen at -2 degrees. And we apply a constant temperature 2 at the top, and also a constant pressure 60 megapascal at the top. So here are the results. So this is temperature, saturation of ice, gradient of water pressure represented by arrow, viscoplastic strain, and the effective stress. If we focus on this gradient of water pressure, we can see that the minimum water pressure always follows the Sowing front in this case. And if we look at the viscoplastic strain and effective strain stress, well, the viscoplastic strain on the top part actually diminish because of the thawing of the ice. And also we have this stress relaxation on the top. Let's look at it again. So here are the summary. We have derived and implemented a fully coupled thermal hydromechanical formulation using dual skeleton solid approach, which considers ice as solid. We capture the effect of viscosity and anisotropy for ice. And our model can capture freezing and the thawing process of soil with cryosuction naturally induced. And we want to validate this model with experimental result and explore the effect of anisotropy on the freezing of soil. Thank you.